Greetings, everybody. Welcome back to Learning as a Hobby. In this video, I want to continue with what I said in my previous video. The next thing I want to do is Chapter 2 in the Taylor book. So we'll start with 2.1 today. And then once we finish Chapter 2 here, we'll come back to Simmons and Schifrin. So let me bring up my notes for section 2.1. And the reason that I said I wanted to do this is because do this chapter next is because the material here relates to what we did in the last section in the Simmons book. So I figured this would be a good time to do this section. So this is on well, this is what chapter 2 is about. He says it here. So motion of projectiles subject to the forces of gravity and air resistance. Usually in, like a calculus course, in Calculus 1 or Calculus 2, you look at projectile motion, but you ignore air resistance. And I'm assuming it's the same thing in like, a freshman level physics course. So here we're going to include air resistance in our problems. And then also the other thing that he talks about in this section is motion of charged particles in uniform magnetic fields, which I'm not sure I'm going to get to. I might end up skipping that section because I don't actually know anything about electromagnetism yet. So I'll see when I read that, when I skim through that section, I'll see if I feel like I can do the stuff that's in there or not. If I don't have enough background to be able to do that section, I'll just skip it and come back to that maybe once I've learned some electromagnetism. So those are the two things that he talks about in chapter 2. Right. And he says also both of these problems lend themselves to solution using Newton's laws and Cartesian coordinates. All right. So starting in 2.1, which is on air resistance. Whether or not air resistance is significant to the solution of a problem, we'd like to develop some way to estimate how important it really is in the problem, because maybe we can, for example, maybe we can ignore it if it's negligible compared to other things. So the force F due to air resistance depends, excuse me, depends on the speed V of the object. And he says here we'll only consider situations where F and V point in opposite directions. There are more complicated situations where that's not true, but in this section, that's what we're going to focus on. So just to see the picture here, the object here is the circle, the little circle that I have here. Let me bring my pen out. So that's the object or the projectile that's moving. It's subject to the force due to gravity. So, its weight pulls it down. And then this is the resistance force, which is proportional to the velocity, which goes in this direction. And notice that the way that we've drawn it, the air resistance goes in the opposite direction, completely in the opposite direction. All right, so that means that the drag force F will be of the form negative F of V times the unit vector in the V direction, right? The unit vector in the V direction is V divided by its norm, and F of V is the magnitude of the force. Okay, and then he says, at speeds lower than the speed of sound, F of V can be approximated by this formula here, which actually follows from Taylor's, Taylor's approximation. If you remember Taylor series and Taylor polynomials from calculus. So F of V can be approximated by BV plus CV squared. So there's a linear part and there's a quadratic part. The linear part he calls F with the subscript of lin for linear, and the quadratic part is F with the subscript of quad for quadratic. Right. So we can these two terms are what dominate usually in these drag problems, right? And then he just talks a little bit about where these forces come from. The linear term, which has the form B times V, arises from the viscous drag of the medium and is generally proportional to the viscosity of the medium and the size of the projectile. And in the exercises, we'll define exactly what he means by viscosity. And the quadratic term, which looks like this, CV squared, so it's proportional to the square velocity, or the square of the speed, arises from the projectile having to accelerate the mass of air or if whatever the fluid is with which it continually is colliding. It's proportional to the density of the medium and the cross-sectional area of the projectile. Okay. So he derives some important special cases here for a spherical projectile with diameter d. B has the form beta times d. So in other words, some constant times the diameter of the sphere. And C has the form gamma times d squared, where gamma is some constant and d squared is the square of the diameter of the sphere. Right? So beta and gamma depend on the nature of the medium. And we'll derive these things later on in the exercises and so on. Okay, so and then he says for a spherical projectile in air at standard temperature and pressure, these quantities are approximately equal to 1.6 times 10 to the negative 4 Newton seconds per meter squared, and gamma is equal to 0.25 Newton seconds squared per meter to the fourth. Okay, often we can neglect one of the terms, either the linear term or the quadratic term, when one is negligible compared to the other. So if one dominates, the other one, just to simplify the formulas, can usually be neglected, or can sometimes be neglected. But we have to know when we can do that. So he derives a way of looking at that. So to decide if we can, and which one to neglect, we compare the sizes of the two terms. So you take the ratio of the quadratic force divided by the linear drag force. All right, so and by the form that they take, that's CV squared over BV. You can cancel the common factor of V, and then for a spherical projectile in air at STP, you can replace C and B by what we said above, and that gives you gamma D over beta times the velocity. Right, so it's proportional to the velocity and the diameter of the sphere. And we can actually calculate gamma over beta. It's equal to 1.6 times 10 to the third seconds per meter squared times the diameter of the sphere times the velocity. Right, and then we have an example where we calculate some values using that formula. So assess the relative importance of the linear and quadratic drags on a baseball of diameter 7 centimeters traveling at a modest 5 meters per second. And then he wants us also to do the same for a drop of rain, which has a diameter of 1 millimeter and a velocity of 0.6 meters per second. And then also for a tiny droplet of oil used in the Millikan oil drop experiment. Here the diameter is 1.5 micrometers or micrometers, if you like to say it that way. Um, and the velocity is 5 times 10 to the minus 5 meters per second. So just plugging into the formula, you do have to be careful about your units here. So make sure you convert everything so that the units all match. So for the baseball, you just take 1.6 times 10 to the third seconds per meter squared times the diameter times the velocity. Here, notice that I'm converting the velocity. I'm converting the diameter into meters because he gives it to us in he gives us it to us in centimeters. So when you do that, you get 560. So here, in other words, for the baseball, it looks like the quadratic term is what dominates in this situation. So the linear term is, almost, it's completely negligible in this case. So what the only thing you really, if you're modeling this situation, it's probably okay to just ignore the linear drag and just focus on the quadratic drag in that case. Right, for the raindrop, again, just plugging everything in and making sure all your units match, you get 0.96. So it's very close to 1. So here, for this example, you probably can't ignore either of the drags. The linear drag is just as important as the quadratic drag. So that's a much more complicated situation. You can't ignore either one. And then for the oil drop, again, plugging in the values and making sure your units match, you get something very tiny, which means that the quadratic term is completely negligible compared to the linear drag. So you can ignore the quadratic drag in this case, which makes the situation a little simpler. Right, now, notice for macroscopic objects like the baseball, the thing that makes a difference is the quadratic drag, which makes the model's more complicated to solve, unfortunately. So, and then here I'm just saying that for the baseball, the linear term is negligible. For the raindrop, neither is negligible, and for the oil drop, the quadratic drag is negligible. Okay, last thing he talks about in this section is the Reynolds number, which is a quantity that allows you to decide, which of those you can ignore in a particular situation. So recall that the linear drag is related to viscosity of the surrounding fluid, and the quadratic drag is related to the inertia and hence the density of the fluid. Okay. So the quadratic drag over the linear drag, the ratio of those two is related to the fundamental parameters eta, which is the viscosity, and q, which is the density of the fluid. Okay, so that means that the ratio of the quadratic drag to the linear drag is roughly the same magnitude, not the same number, but the same magnitude as what's called the Reynolds number, which is given by this formula here. The Reynolds number R is dV times Q over eta, which means that the quadratic drag dominates when R is large, and the linear drag dominates when R is small. So this gives you sort of like a test for when you can ignore certain terms in the drag force. Right. I think that's all he talks about in section 2.1. It's a relatively short section. So I'm going to end this one here, and I think I'll immediately do the let me just stop the screen share. I'll immediately go through the exercises for this section. There's only 4 problems, so, and they're relatively short. So I'll go through those in the next video. I'll post those right afterward. And I'll see you guys in the next video. Keep learning.